one day, I got a really splitting headache, which I don't usually get. I mean, it was a really splitting headache. And then after I had this headache for about a half hour, an hour, I realized what had to be done, what was the general formulation and how to prove. It wasn't really so difficult. So I never had that headache again. Calderón had been working on what was then later known as the Calderón commutator theorem. And that developed into the proof of the Calderón's version of the Cauchy integral. In this commutator theorem, the basic fact was to prove that there is some operator, you want to prove that it's bounded on L2. And so I was thinking, maybe there is a general sort of L2 theorem that can be used to prove that that operator is bounded on L2. So what could that L2 theorem be? And so I remembered Cutler's lemma. So I thought to myself that if only one could find a non-commutative analog of Cutler's lemma, then one could do this Calderón commutator theorem. It just so happened that at that time, Cutler had a position in Rutgers. And I said, Misha, you know, you're a nice theorem. I think there is a non-commutative analog. And if that non-commutative analog holds, then I think we can prove the Calderón commutator theorem. And I was very excited, and I was going to tell Cutler, but Cutler called me up and he told me he had also found a proof. So we had both found essentially the same proof at the same time.
By a particular way that you lecture and the way that you teach, there's tremendous work to find exactly the right point of view.
When I teach, I'm always thinking about how would I have liked to have learned the subject. What I like about mathematics is the interplay with other people. And that generates extra energy because it really helps you think. I mean, you say something and then later the other person says something and then it just all works so well. And there's nothing like it.
How did you get interested in math?
Well, I got interested in math in high school. So first I went to this high school, which was quite good school, Stuyvesant High School in New York. And it was during a course in plane geometry. So we had a very good teacher. His name was Mr. Schwartz. And what I really liked about geometry is that it was very deep. The previous course was algebra, and we manipulated x squared, and solved quadratic equations. It seems sort of trivial and not very interesting. But here, we proved what seemed deep theorems, starting with axioms. And this Mr. Schwartz, he had this just fantastically high regard for mathematics. One day he said, the most wonderful part of mathematics is, and he said, you are too young to know about this. It's the theory of elliptic functions. Of course, I didn't know anything about elliptic functions. Then a few days later, he came and he brought a book and he said, this is a book about elliptic functions. And I looked into it. There were all these mysterious symbols, magical. And it turned out, I think later one of them was the pay function. The other one were these big S's, these integral signs. And this must be something really wonderful, I thought, and deep. That was one thing. And another thing was, he told us about a theorem of Steiner, which was not part of the curriculum. And it had been proved, not by the Greeks, but by Steiner in whenever it was in the 18th century. And it was the theorem that if you had a triangle and two of its angle bisectors were equal in length, then the triangle was isosceles. And he gave us a thing to read. I read it. It was a very, very ingenious proof which required a construction, you know. You can't just look at this triangle with the angle bisectors, but you've got to make a further construction, and then you... And so I felt very challenged by that, and I said to myself, I'm going to try to find another proof of this theorem. Little did I know, so I struggled for many weeks. Finally, I did find a proof, but I must say the proof was very inelegant, not like Stein, and it was very complicated. It sort of instilled in me the confidence that I could do some mathematics. I think the other very important thing for me was that there was a math club at Stuyvesant and a math team where we competed. And the captain of the math team was D.J. Newman. At the time I joined, and he was quite a mathematician. Anyway, as a student then, he was extremely impressive because he seemed to know everything, and everything was very easy for him. To feel that you're really part of that group that existed then, there were two things, roughly, but my memory is maybe vague, but there were two things you had to do. One was you had to read you had to learn some advanced mathematics on your own. And one of the things people did is they read Titchmarsh, Theory of Functions.
In high school?
Yeah, of course. You know, there was much of Titchmarsh that I didn't understand, but I was exposed to Titchmarsh. And from then on, I knew that that's the kind of mathematics I liked. And then there was another thing. The other thing is there was Barnes & Noble's in those days was a textbook store, a unique textbook store, not far from Stuyvesant High School, I think on 16th Street and between 6th and 7th Avenue.
Oh my God, it's still there, I think.
And the idea was that you had to steal a math book from Barnes & Noble.
Yeah.
That is something I did, as it turns out. It wasn't a very valuable book. But those are some of my earliest memories of getting interested in mathematics.
Let's fast forward. You're at the University of Chicago.
Yeah, maybe I should say why I chose the University of Chicago, because in those days, all the people from the math team who were interested in mathematics, they all went to Harvard. But I had this failing. I had a lot of trouble getting up in the morning. I would always sleep very late. And so I didn't want to go to a college where classroom attendance was compulsory, as it was, or it's still in those days. But the University of Chicago, in one of their advertisements for the college, was that nothing counted in a course except for the final exam. And I felt I could then do that. I wouldn't have to go. And of course, it had a very good reputation because in those days, the atom bomb, and it was all of that. So that's how I got to the University of Chicago. So once I got to the University of Chicago, after a while, I, of course, drifted to Zygmunds, because that was the kind of analysis that...
Now, maybe that's not such a simple story, right? Whom did you meet? What did you consider?
The first 2 years, I was in what was called the college, which was the undergraduate part. There was a one math course that you had to pass, in which I placed out of in the college. It was sort of very general, very soft, very general mathematics, a little bit about the definitions of rings and fields and groups and sets. So there was nothing challenging there. So I decided to try to take some graduate courses while I was an undergraduate. And One, I took a course with a Spaniard who was a topologist, who later went to Berkeley from Chicago. And this was a soft course in functional analysis. And it culminated with the Stone-Weierstrass approximation theorem. I liked it, but I was not enthralled by that. But except for that, I didn't have much contact. And then after 2 years at Chicago, I had to go back, and because my parents refused to support me anymore. They said they would only support me if I went to Columbia, because we lived in New York. So I had to go to Columbia, but not as an undergraduate, but as in their extension school. So I spent a year there, and I took some very good courses, actually, because they let me do anything because I wasn't a degree student. So I took a course with Harishchandra, who was then at Columbia, and a course with Lorch, which was a nice course, even a course with Sammy Eilenberg, but I didn't understand anything. I mean, Sammy Eilenberg was lecturing. He had just written a book, or was just writing a book, and on topology. I think it was with MacLean. And it was about axiomatic algebraic topology, and he started off right away with the axioms and discussed. They make sense to you only if you really understand the subject, and of course, so I did. Anyway, so when I came back to Chicago, the year afterwards, I was able to get a fellowship. So I came back to Chicago, and I immediately sort of drifted into the orbit of Zygmunt. And then I took a course with Zygmunt. It was a course on approximation theory. And it was very elementary. So there was the circle, the functions on the circle, and there were trigonometric polynomials. And the question is, how well can you approximate a function by trigonometric polynomials, and how quickly does it work? Well, of course, if it's in the L2 norm, it's the partial sums of the Fourier series, and that's clear. So what happens if you're trying to do the best approximation for degree n of a polynomial, but in the sup norm? And there were sort of classical theorems about this and other theorems, and the course was made up. So after about a month, Zygmunt said, well, there's this following very interesting problem. He said, okay, so if you have a continuous function, you can talk about the polynomial of degree n, the trigonometric polynomial, which is the best approximation in the L infinity norm. It turns out it's unique, okay? That's one of the theorems you can prove, okay? Now, here's the question. Suppose a function is not merely continuous, but is differentiable and has a derivative which is continuous. Take this sequence of approximating functions. Do the derivatives, the sequence of derivatives, converge uniformly to the function? He said, that's a very interesting and difficult problem. So I thought about it a little bit. I don't know. I paid close attention to what he had said earlier in the course, which was something about the delayed means, which are the things where you approximate. So the Lavallee-Poussin delayed means. And then I realized that by using these things, you could give almost a 3-line proof of this theorem. Yeah. So I came to Zygmunt and I said, Professor Zygmunt, the question that you raised, I think it has a simple answer. He said, no. Now think about it again. But he didn't want. So then I came back and I said, no. And finally I told him, and so then he was very nice about it. And then a few days later he said, you're a real mathematician. And so that was a very, very nice thing. I, of course, clearly became Zygmunt's student. He had a large number of students. There was a group of people. Some of the people who were students just at the same time as I was as a student were Guido Weiss and Mary Weiss.
And these people were grad students also.
Yeah, so what Zygmunt had is he had his seminar. And part of what he did when he had many students, which he did at that time, is that he would assign a topic to each student. Read a paper, a particular paper that's been around for a year or 2 or 3, and you were supposed to present that paper, and then the idea was that once you got to know the subject a little bit, maybe you'd work on that subject. He was not very good about assigning you a problem. I mean, it was more that you sort of hung around him. He had certain attitudes about mathematics, you know, certain points of view, which he stressed, and those were very important. But as far as assigning problems, he never assigned me a problem, except that he asked me, and this was very important, he asked me to talk about interpolation theory. So Calderón and Zygmunt had just a year or 2 before written a nice paper on the Riest-Thoren interpolation theorem. So I gave this talk. I wrote a thesis on some minor series of little results on my own.
Yeah.
Then he looked at it and he said, okay, that's enough for a thesis. That was it. I mean, he wasn't really very interested in it. But one of the things that Zygmunt was always coming back to was the 2 things. One, we wanted to talk about various extensions of Fourier analysis from one dimension to higher dimensions. So part of his point of view was, in one dimension, what he called complex methods were fundamental. Complex methods meant that you had the unit disk, and you had holomorphic functions in the unit disk, and the methods which used conformal mapping or various other things were very important in proving theorems about Fourier series. Now, he was very interested in higher dimensions, and of course, you couldn't use complex methods. So you had to develop what he called real methods. And of course, at that time, he was working with Calderón, and they did this theory of singular integrals, which extended Marcel Ries's theorem about. So he was always complex, the passage to several variables and the idea of developing real methods was very important. So I started to read about multiple Fourier series. And I read a paper of Bachner, which I liked. So I started to talk to Zygmunt about it, and he didn't think that multiple Fourier series was an interesting subject. He thought it would be sort of a routine extension. Maybe I'm not doing justice to what he really had in mind. But it would be a routine extension of the one-dimensional theory.
So on the one hand, it's very important to extend from one dimension to n dimensions, but on the other hand, multiple Fourier series were routine.
Well, because when he thought about Fourier series, he also thought about these various questions about convergence, and what you can find in his book, Trigonometric Series. So you can, if you look in that direction, maybe he was absolutely right, but it depends where you look. So anyway, he didn't think it was so interesting, but I thought, and I learned from Bachner the following thing, which was that in higher dimensions, what Bachner called, there was a critical index, and the critical index was n-1/2, where n is the number of dimensions, because summability, Bachner-Riest summability, above that order was like the usual thing in one-dimensional Fourier series, and below that order, it was very mysterious. Nothing was said, but of course it was clear that for order 0 L2 or order epsilon, various L2 theorems held. That was clear, but maybe that wasn't stated. So that was something that I thought about. Well, anyway, then there was one summer in 1955. He said, I'm going off to Ithaca for a month to visit Marquette. He said, what are you doing then? Of course, I said, I'm not doing anything. So he said, come to Ithaca. So I moved to Ithaca for a month, and I saw him from time to time. But then in the library there, I realized that my interest in interpolation theory fitted into exactly into that problem because the critical index was good for L1 or something, and there was the L2 theory, so there should be something in between, and so you should be able to interpolate this result, and so you should be able to use operators that depend analytically. So that worked out very well.
Everybody thinks so.
In those days,
Yeah.
it's quite a while ago now, collaboration was not the same as it is now. I mean, first of all, it was harder and it wasn't done as much.
Yeah.
Some people collaborated, but still, most mathematics was still being done in a solo way. Now it's all different.
Yeah.
Guido Weiss was one of Zygmund's students, and I was very friendly with both Guido and Mary Weiss, and so Guido and I started to talk about things. And one of the questions we were interested in is there was a mathematician, a British mathematician, whose name was P. Stein, no relation. I think he was a student of Hardy. And he had found a proof of M. Ries's theorem that uses the fact that the Laplacian of an analytic function, absolute value taken to the pth power where p is positive, is still positive because it's subharmonic. And inequalities relating that and the Laplacian of a harmonic function raised to the pth power. And so we sought to generalize that to higher dimensions because, again, it was extending things to higher dimensions. And so we found this nice result that if you take the gradient of a harmonic function and raise the pth power, then it's subharmonic to powers p for p less than 1 in higher dimensions. And so that's how we started the theory of HP spaces in several variables. Of course, in a way, the theory wasn't completed until you, Charlie, came along, and we worked on it. But a very important thing that happened was, of course, your work on duality of H1 and BMO, which was the spark that led to, I think, the culmination of that. Well, anyway, so that was one line of collaboration that was very important to me. There was another line of collaboration. There was another student at the University of Chicago at that time, Ray Kunze. He was a student of Irving Siegel. And Siegel was a very nice man, very nice guy. He was very nice to his students, and he wanted me to be his student, clearly, but I was already committed to Zygmunt. I met Leon Ehrenpreis, who I'd known, by the way, when I was at Columbia for that year that I had mentioned, and he and I were both students in Harishchandra's course. He got his PhD in Columbia with Chevalier, the year after I was there as a student. Leon asked me the following question. He said, I'm working on SL2R, and here is something about harmonic analysis on SL2R. He said, what is the analog of the Hausdorff-Young theorem for SL2R? So, of course, Hausdorff-Young is something, I knew from the very beginning when I was in Zygmund's, when I lectured in Zygmund's seminar on interpolation theory. So I thought about it, and I realized that this theorem about analytic families of operators allows you to prove sort of a rather unexpected Hausdorff-Young theorem where you now have functions, it's functions which are holomorphic in strips, and there's some HP theory for that.
Can you say a little more about the train of thought, right? That's very radically different.
Here's the train of thought. If you look at the analysis on this group SL2R, then for L2 you have a Plancherel formula, except that what it's indexing is not the Fourier transform is not indexing numbers, but it's indexing infinite dimensional, unitary, operators. Okay, so But there's a strip, and that's along the central line of the strip. But if you have a function in L1, because there are these large class of uniformly bounded representations, then you get automatically a holomorphic function in a strip.
Yes.
So for L2, you get an L2 function along the central line of the strip. And for L1, you get a holomorphic function in the whole strip with a certain bound. So for LP, you should get a holomorphic function in a narrower strip depending upon P. So that seems reasonable. And then you have to just work this out. And that worked out very nicely. And so that had a lot of very nice consequences. Right. That collaboration was a collaboration with Ray Kunze. Ray Kunze had been a student of Siegel, and he was interested in that. So we naturally talked about it, and we wrote several papers about that.
We have the dual expertise, right? So representation theory and classical analysis.
Yeah, which I then pursued later. My interest in representation theory I pursued later with Tony Knapp, because when I came to Princeton, Tony Knapp was a graduate student here, and so we started to talk. I got my degree in Chicago in '56, and then I spent 2 years at MIT, and then Zygmunt arranged for me to come back to Chicago. So I was there with him, and then a year later, Calderón came to Chicago, and there was this great atmosphere, and I was very happy there. One of the things that I was interested in was the following thing that I had noticed. There was Kolmogorov's first proof, that was the first proof, of the fact that the Hilbert transform was a weak type 1-1. It wasn't anywhere like the standard proof. It went the following way. You have a function which is in L1, and by using complex methods, you can prove that the holomorphic function, of which this is the real part, has non-tangential limits almost everywhere. Okay, so the Hilbert transform exists in some sense almost everywhere. From that very fact, he was able to prove by some very clever argument, which fascinated me, he was able to prove that the operator had to be of weak type 1-1. Well, that's sort of something that stands by itself. And then I learned of something else. Calderón had recently proved the following thing. A big unsolved problem was the convergence of Fourier series in L2, 7 years before Carlson's theorem. Anyway, but he had proved the following result. If it were true that the Fourier series of every L2 function converged, then it would automatically be true that the corresponding maximal operator for the partial sums would be of weak type 2, 2. So I looked at these two theorems. They had different proofs. They seemed to have special proofs designed particularly for the operators in question, but I convinced myself that they could not, it couldn't be an accident that there was some general principle. And so I worked very hard on this, and I remember one day I got a really splitting headache, which I don't usually get. I mean, it was a really splitting headache. And then after I had this headache for about a half hour, an hour, I realized what had to be done, what was the general formulation and how to prove. It wasn't really so difficult. So I never had that headache again. But that general formulation was then later called the Nikishin's theorem or whatever. It's a theorem about, it's the maximal principle for that thing. Zygmunt was always talking about the idea that one needed to develop real methods. And so at that time, which was, I had come back to Chicago, so this was about 2 years after my PhD, and Guido and Mary Weiss were still in Chicago. They had gotten their degrees, but they were teaching at DePaul University. And the three of us would meet often with Zygmunt and sit in his office for an hour or two and chat. Zygmunt said there is this interesting problem. So you have to go back a little bit. So when Zygmunt had Calderón as a student about 9 years before, and one of the results that Calderón obtained in his thesis, which is quite remarkable, is a partial extension of the one complex variable thing to higher dimensions, the theorem of which had been proved in one direction by Lucene and in the other direction by Don Spencer. And it was the following theorem, that if you have a holomorphic function in the unit disk, and you ask the question is, does it have non-tangential limits at points on the boundary? That's one question. And the other question is the what's called the area integral of Lucene finite at almost every point of that set? And it turns out that the sets at which the non-tangential limit existed and the area integrals are finite are almost everywhere the same. This is a remarkable theorem proved in one direction by Lucene and in the other direction by Spencer. And typically, this is the use of complex methods, and there's a sort of a star shape. There's a jagged kind of domain, and you use conformal mappings. You use the whole machinery. So a fascinating problem for Zygmunt had been, what's the higher dimensional real analog? And he had given this problem to Calderón in 1950, and Calderón had solved half of it, and that was partly in his thesis. That was the direction that if you had a harmonic function in the upper half space and it had non-tangential limits on a certain set, on the boundary, then almost everywhere the corresponding area integral was finite. And so Zygmunt said, well, there's the proof of the converse, which will need entirely new ideas. So we talked about it for a while. And so after a while, it occurred to me that maybe it does not really need such new ideas. Maybe I can do it. Yeah. So at one of these meetings, I said, well, I think this can be done. And I sort of outlined very vaguely a project of how it could be done. And Zygmunt said, no. This is going to be done by some person who has really new ideas. Okay, so we left it at that. Now, this was March of 1959. Yeah. So Ellie and I were going to be married in New York 2 weeks later. Yeah. Okay. And so I was going to travel to New York. We were going to get married in New York, have a small little wedding. I mean, just family. And then we were going to make a little honeymoon trip. And then I would come back to Chicago because this was in the break between the two quarters. And she would go back. She had another semester of teaching to do. She was teaching school. Then later she would join me. And since I was going to be flying back to New York for this, Guido and Mary were going to borrow my car. I had a 1956 Chevrolet. They didn't have a car, and they wanted to take a trip. They were going to go to Virginia or something, and they were good friends. They went off. I got married. Even though I was on my honeymoon, I couldn't stop thinking about the problem. I mean, it wasn't very, as it turned out, I had the right idea, but there was one point that I didn't see, and one day, among all the other things, it clicked. Yes. And so when I came back to Chicago, I was also, of course, very happy about how things had gone, but I had this nice theorem now. I met Guido and Mary because they were going to give me back my car. And then they said to me, have you heard? Have you heard? They were very upset. He said, have you heard? Well, Zygmunt had gone off during that week. Zygmunt had gone to visit Calderón.
Yeah.
Calderón was then still at MIT.
Yeah.
He said, have you heard? Calderón has proved this result.
Yeah.
And Zygmunt had talked to him, and
Yeah.
Calderón had proved it.
Yeah.
And they were very upset that Zygmunt had talked. And
Yeah.
I was very upset too. And anyway, so when I met Zygmunt, I don't know, I didn't control myself very well, and I got quite angry with him. I mean, I'd never had such a
Confrontation with.
right with him or
Yeah.
almost any other mathematician. But then within a week or so, we patched it up, and we never spoke about it again.
Yeah.
Of course, Calderón, when he found out about it, because he was an innocent party in this, he didn't know very much about it. I think what happened is that the fact that I talked to Zygmunt and I
Yes.
expressed some feelings about it, he then told Calderón, and Calderón had a solution to the problem, which technically was different from mine.
Yeah.
But, you know, it was in the same mindset. But he was innocent. And he was very nice about it because he told me, he contacted me on his own and he said, oh, never mind, I'm going to withdraw. I mean, I have no role in this. So anyway, and Zygmunt and I patched it up. I mean, I went to Zygmunt and I said, I'm sorry I spoke so harshly to you. And we never talked about it again.
Can I ask, what did he say at the time? I must say, I haven't been on the receiving end of a confrontation like that. I wonder what it's like.
He was sort of shocked that I talked to him like that. I mean, I think that's what I remember. He didn't try to say, well, I didn't say anything or anything like that. He just sort of, you know, I mean, you know, I had never, you know, I was always very respectful. You know, I held him in very high regard, and I was always deferential to his opinions. But in this thing, I felt he had betrayed me in a way. After about a few days, I called him up and I said I would like to come and talk to him. And I went to his apartment and he offered me tea and we chatted. But we didn't chat about it directly, and that was it. And I think, you know, he did not mean any harm. What I resented was his feeling that I was not good enough to solve. I mean, he didn't say that.
I see, right.
That I somehow, when I originally presented the idea, okay, maybe it's not so great. I mean, it was a twist on older ideas. I can explain what it is, but maybe it's not so important. But that he felt that, you know, I wouldn't be able to do it. This became a little part of our collaboration on HP. So it was, everything worked out.
No, I remember learning these things from you in
the end, everything worked out well.
I mean, these things, the mathematics, not the human element.
Even that worked out well. No, I have very fond memories of Zygmunt. Another thing of Zygmunt that I learned was this thing about the Littlewood-Paley theory. So Zygmunt spoke about this again with great admiration. There was this theory, again, in one complex variable. I mean, basically, it used much of one complex variable. And so, of course, at the same time, he was talking about the theory of singular integrals. And so one of the first things I felt very challenged was to try to do some of that Littlewood-Paley theory by the methods that they had used in the theory of singular integrals. And I was able to do that, and so that was very important for me.
Can you say anything about the thought process by which you solved it?
These operators, though they were nonlinear, the square functions, were in many ways not so different from the singular integrals. I didn't really see this very clearly. After I had done my work, Jack Schwartz and Lars Harmander realized that these were just vector-valued versions of the theory, and everything became very slick, and it all became, obsolete. But I had to struggle because I didn't see it that way, so I realized that the weak type estimates should hold, and I proved those.
So they were not known for...
No, they were not known.
In n variables or in one variable?
They weren't known in one variable. There was nothing known in n variables.
Yeah.
I mean, even the operators hadn't been formulated. Only one of those operators had been formulated. That's the Leucine area integral. It had been formulated by Calderón when he proved the thing I mentioned before, the finiteness almost everywhere. But the other operators hadn't been formulated. And so the proof that existed was by complex methods. And there's no simple complex method proof for weak type 1-1.
In the early 60s, maybe you were back from MIT, you were in Chicago.
Yeah, and I'm about to go to Princeton.
Yeah.
So I come to Princeton, I have to say, partly because Ellie wanted to go to Princeton. I did not want to leave Chicago. I was very happy in Chicago. I had been an undergraduate and then a graduate student. I came back on the faculty. Everything around, there was Calderón and Zygmunds and other people. But Ellie, I think, rightly thought that Princeton was a nicer place to live, and we had small kids, babies. So the first year was the academic year 62-63. I was on leave from Chicago. I was at the Institute. And at the Institute, there was this atmosphere that emanated that I felt was very unfriendly from point of view of analysis. I mean, it was, cohomology, functoriality. I mean, that's what you had to know. That was the language you had to speak in, or maybe some number theory. But analysis was sort of advanced calculus. So that was very unfriendly. And it sort of permeated a little bit into the university, too, because, I mean, the senior people at that time at Princeton were Bachner and Feller, and they were not so active anymore. And of course, there were the younger people. Hugo Rossi had been, he left just the year before I came. Also, Don Spencer left the year before I came. But there were other younger people, but it wasn't the same. The weight that I felt of sort of being isolated as an analyst. There was Ed Nelson and Bob Gunning, and there was David Laudenslager too, who passed away within a year. Things didn't change for me until I began to have students, particularly you, Charlie. That began to change the atmosphere of analysis.
You changed the atmosphere.
No, but I mean, it made a great difference. Another thing that made a great difference was that about that time that you were my student, that's the time that Don Spencer and Joe Cohn came back. And Don Spencer was a very nice guy. I didn't have much really mathematical interchange. With Joe Cohn, I think it was more important. My first year, I think it was, when I was in Princeton, Joe Cohn was at Brandeis at that time, and he came to give a lecture. And I think he was lecturing about work that he had done with Hugo Rossi. Anyway, it was about D bar B. I didn't understand very much about D bar B. I didn't know anything about several complex variables, I have to say, because where I was brought up, one didn't mention it, it didn't exist. One complex variable, yes, but several complex variables, nothing. But he said something which struck me. It seemed that in several complex variables, as opposed to one complex variable, if you have a holomorphic function and you look at its boundary values, which of course, for a harmonic analyst, this is what you want to do. You can characterize those functions by the fact that they are solutions of differential equations. And that is totally unheard of in one variable. So that was one thing that struck me greatly. Another thing that struck me, I think it was about a year later or 2 years later, when Joe Cohn came. And of course, there was the D-bar-Neumann problem. Again, I didn't know anything about the D-bar-Neumann problem, enough to know that it was some kind of a boundary value problem. And he said to me that he wanted to apply the theory of pseudo-differential operators to this boundary value. Of course, theory of pseudo-differential operators was, of course, closely related to the theory of singular integral operators, but it had been put in a form which was very good for PDE by Joe Cohn and Nirenberg, and worked out, also generalized by Homander. So there was this theory of pseudo-differential operators, and how do you apply this theory? The question was, how do you apply this theory of pseudo-differential operators to solve the D-bar-Neumann problem? And Joe said he had tried several times and it didn't seem to work. All right, so now I want to connect with a different strand of interest. So as I said, I had been interested in semi-simple Lie groups, which I had worked with Ray Kunze. But then after a while, I started to work with Tony Knapp on the subject. And we started to look at the totality of semi-simple Lie groups, even those of rank 1. And among them was the group SUN1. And the group SUN1, the basic nilpotent group associated with it was the Heisenberg group, in the same way as for SON1, the Euclidean thing. Now we are in the 70s or the late 60s. One had to prove that certain operators were unitary. So maybe I will come to that story in a moment. That was the challenge. But anyway, I had learned about the Heisenberg group. And I realized that one could not do pseudo-differential operators, which was like Rn, but one had to do the class of operators which were like the operators on the Heisenberg group, with their own kind of dilation structures, that those were the right operators. And that started off with work with Folland, and that turned out to be very successful. But I want to come back to just one other strand of this, which was what's called Cutlar's lemma. So Cutlar was a graduate student, a somewhat older graduate student. He had already worked on many things in mathematics, of Zygmunt. And he came to visit Chicago at the time I was a graduate student. I don't remember exactly when, but he had already gotten his degree. And one of the very striking things that Cutlar had done was Cutlar's lemma, which was a proof of the boundedness on L2 of, let's say, the Hilbert transform without the use of the Fourier transform. And it was a nice decomposition of the operator into different dyadic pieces which almost commute and satisfy some orthogonality principle. And then, sometime in the middle 60s, there's a whole interesting strand of mathematical development. Calderón had been working on what was then later known as the Calderón commutator theorem. And that developed into the proof of the Calderón's version of the Cauchy integral and all that great development that took place. But in this commutator theorem, the basic fact was to prove that there is some operator. You want to prove that it's bounded on L2. And it's not your usual convolution operator. And of course, that L2 is the key point here. So you need to have an L, because once you know how to prove that it's proved in L2, then by what's called the Calderón-Zygmund paradigm, it's bounded in LP. So Calderón had a very nice, ingenious argument, but it was very special to this operator. And so I was thinking, maybe there is a general sort of L2 theorem that can be used to prove that that operator is bounded on L2. So what could that L2 theorem be? And so I remembered Cutler's lemma. The only problem was that Cutler's lemma was the operators in question basically had to be abelian. They had to commute. And one way to see Cutler's lemma, even though he had a very complicated proof originally, is by simultaneously diagonalizing these operators, and then it's quite easy. So I thought to myself that if only one could find a non-commutative analog of Cutler's lemma, then one could do this Calderón commutator theorem. It just so happened that at that time Cutler had he spent a few years in the United States, and he had a position in Rutgers. And one day, I think I went to Rutgers for whatever reason, either to talk to him or we met. And I said, Misha, you know, you're a nice theorem. You know, I think there is a non-commutative analog. And if that non-commutative analog holds, then I think we can prove the Calderón commutator theorem. So that was our conversation. And then I went home, and like in many of these things, when you talk to somebody else about some idea you may or may not have, just by talking about it, you think about it. And I thought about it, and I realized how to prove the theorem. And I was very excited, and I was going to tell Cutler, but Cutler called me up and he told me he had also found a proof. So we had both found essentially the same proof at the same time. But before I talked to Cutler about it, I tried to use it to prove the Calderón commutator theorem, and he had also tried it, and we both failed. Okay, the upshot of the story is that a number of years later, David and Journet proved the T of 1 theorem. So the thing we were missing, they found, and they used this argument together with, and the T of 1 theorem then gave a quick proof for that thing. And of course, that was very important in other developments.
Tell us something about your discovery of new families of representations.
I told you something about SL2R and how in SL2R it's pretty clear that there's an analytic continuation of the principal series, and that leads to complementary series, and that's very important in the analysis of representations leading to functions which are holomorphic in strips. And so the natural question was, what were the representations that you got in other groups? And could you do this analytic continuation? And so we found, first working with Ray, and then Ray Kunze, and then with Tony Knapp, that there were representations, complementary series, which meant these were analytic by introducing the right kinds of objects. You could do their analytic continuation, and you could obtain unitary representations, which you could prove are irreducible. And then you could look at the book of Gelfand and Neumark on the classical unitary representations of the classical groups, and you could see their list of what were purported, the complete list of representations, and you could find representations constructed this way, which were not in their list.
Am I right? Other groups had done it independently?
No,
do I have that
no,
wrong?
no. Only they had claimed.
Yes.
And they had not given a proof.
Yeah.
There was that style of mathematics that existed at that time in that subject, where often you gave proofs for many theorems and you had ideas, and then you sort of claimed theorems which you didn't prove. And I think that existed in their circle. So I don't know of anybody who was at that time proving that all. You see, it's very hard to prove that you have a complete list of unitary representations. It's easier because there's the algebraic problem of when you have a representation,
Yes.
and that you could maybe reduce to a question of an infinite dimensional Lie algebra problem. But to know when that representation can be unitarizable
Yes.
is a more difficult problem. So it would be much harder to have a complete list, even though they claimed they had and there was no contradiction until it was pointed out.
What was the prevailing view, and what was your particular view? Did you just, right from the start, not take for granted that they were right?
I think with us, it was, I have to say, not our goal to
Yeah.
prove that. It was something that incidentally came out of our work.
Yeah.
And it was the part that was easiest to talk about, because what we were proving is that there existed certain analytic families that had various properties. But if you look at these analytic families of representations, you find these new representations there. But our goal was to understand these analytic families. But if you tried to explain these, nobody, their eyes would glaze over. But if you told them you had some new representations, they would say, oh, that's interesting. In 1976, I was invited, it was a sort of a self-invitation arranged by the Academy of Sciences to visit the Soviet Union, okay? So at that time, if you wanted to visit the Soviet Union, the Academy arranged it, but you had to list the mathematicians you were going to visit. And one of them that I certainly wanted to visit was Gelfand, so I wrote down Gelfand. And for some reason, the Academy's application for this visit was turned down by the Soviet Academy.
It was turned down.
Yeah. And so then the National Academy decided to make a very big fuss. I'm not quite sure why it was turned down. I think it had something to do with the fact that Gelfand did not answer when they asked him, or maybe because Gelfand was in bad odor. I'm not quite sure. Anyway, it was arranged, and after being in Moscow for a few days, and we were walking with whoever our guide was, and there was Gelfand walking.
Yeah.
I didn't know him. I had never met him.
Yeah.
With a few, he was always surrounded by his group. And so I met him on the street, and we shook hands and introduced. So he said, yes, you were supposed to come. And he said, why don't you come to my apartment tomorrow and we can talk mathematics. So I came to his apartment. By the way, it turned out to be a day-long conversation without end. I mean, once we started. But it started in the following way. He started by asking me sort of somewhat sharp question. He said, tell me, are you interested in anything outside of mathematics? So I said, yeah. I said, do you like poetry? Then he started, do you like music and something? So then, I answered him, yeah, poetry, I know some poetry, and music I do like, etc. Then I asked him, why are you asking me all these questions? Yes. So he said, well, from your work, I had the impression that you're sort of a narrow, pedantic kind of mathematician. So I think this goes back to the fact
he was
that
threatened.
Yes,
he was threatened.
But somehow I was sort of quick on my feet, and I said something which I really meant sincerely. I said, no. I said, I have such great admiration for you, because I had read his book with Neumark, and actually in Siegel's course, where I was in when I was a graduate student, that book was somehow used. And so I said, you are like one of my teachers. You're one of my... After I said that, oh my God, the whole world opened, and he was full of praise and just wanted to know, what did I think about this and what did I think about that? And everything was hunky-dory. And then I gave a talk to the Moscow Mathematical Society, which is their sort of Moscow colloquium, and
Yes.
he introduced me in a long introduction in Russian,
Yes.
which was
Yes.
luckily translated for me as he was
Yes.
introducing me, full of praise, and it went on and on and on. That was a nice little turn of events.
We know stories about Gelfand.
Yes,
Yes.
of course.
Okay.
This just adds to
Yeah.
the lore of Gelfand.
Yeah.
Yes, yes.
I am very struck by a particular way that you lecture and the way that you teach, and I wonder whether it's got to be part of the way you think, which I don't find as fully developed in anybody else, which is that there is tremendous work to find exactly the right point of view, and once you find the right point of view, then everything is clear and often
Well, you put it very nicely, better than, I guess that's my goal. My ultimate goal in teaching, in fact, in mathematics is not so much to solve a difficult problem. I'm more interested in sort of understanding what is the right point of view to understand something, so that I'm guided by that. And so when I teach, I'm always thinking about how would I have liked to have learned the subject. That's how I think about it. When Jeremy, my son, was young, he gave me once as a birthday present the Feynman lectures in physics. I don't know why, but anyway, I was very impressed by these. Of course, I don't know much physics, but the idea that you would give a course which maybe lasted a year or two, which would cover large parts of a field and would not be sort of narrow parts on one subject and on another subject, and which were not, connected. And I felt that this is the way I would like to maybe once give a course like that in analysis, because there were various parts of analysis that were taught. There was real analysis, Lebesgue integration, and then there was very little connection when it was taught, usually made with complex analysis and Fourier analysis, etc., partial differential equations, even though ultimately any working analyst would have to understand these connections. And so I thought about this for a number of years until Rami came along. I got a phone call from Serge Lang, who I used to speak to about various. Serge Lang was extremely opinionated, but usually his opinions were right, as it turned out. So he called up, and he knew I was director of graduate studies at that time, and he said, well, we have this undergraduate at Yale, and he is really fantastic, and you must admit him. You must. He's the best. He's the best. So, of course, we admitted him, and it was Rami. And after he was here about a year, I didn't really know him that well, but I got to know him a little bit. And he said, do you think you can find something for me to do, which is, he didn't want to just do grading or in calculus or something else like that. So I said, I have this idea, let's talk about it. I want to write these books. Would you? I guess I had known he had collaborated with Serge. I said, would you like to talk about it? And I remember we went to lunch at the Woodrow Wilson, and then we talked, and it was all very natural, and he was very interested. And then we decided to give this course and these courses, and that we would write these books together, and it was a great adventure. So, again, the idea was to teach mathematics as sort of emphasizing the important ideas, not so much. I mean, so for example, the first book, I wanted to teach some of the nice things about Fourier analysis, but if you have to teach that, usually you have to have this dry course on Lebesgue integration first, then some functional analysis. And by the time you've seen that, which is very dry, you don't see any examples of that, you don't really see much of the need, and you don't care. So the idea of the first book was to do it without Lebesgue integration. So that was a little bit of a challenge, but it could be done. And so, I mean, that was always the idea of those books.
Now, as you wrote the books, also you taught the courses,
yes.
Right? So how did that play out?
It worked quite well. In fact, it made it possible to write the books, because what happened is at first there was no manuscript. So the very first thing was the course, and as the course was being given, we had worked out some outline of material. Some of it was detailed and some of it was not so detailed. So as the lectures were given, a set of notes were developed, and those were the first notes on which then the book was written. Yeah. So that it sort of went, the two went together. So, but of course the books were elaborated quite a bit. I mean, you know, there was much more material in the books than could be put in the lectures to begin with. We had some very good students, outstanding students. That was very important.
Among those students was Lillian Pierce, who was very discouraged and seriously considering dropping math, and who was inspired to stay in by a comment that you made that in fact she had the talent to succeed as a math major, and by those courses.
Yeah, right.
Okay, and the other is that Rami continued to collaborate on this project with you long after he got his degree.
Yes,
and
with you.
Through.
He was your student.
Right, he was my student, but through thick and thin, he was devoted to this project. In particular, he had a finance job at Lehman Brothers, and when Lehman Brothers went bankrupt, he continued to work on this project.
Yes, right. We continued to work on it. And we're still not finished because there are always these corrections and other things.
Oh, so maybe there'll be a second edition?
No. Oh, yeah, there's further printings. Because they do sell 1,000 or 2,000 copies.
About the style that I think is obvious to all your students and all the many people you've collaborated with. Optimism, right? If you don't have optimism, you have no chance. Math is hard, and you convey it. How the hell do you do that? Well,
I don't know. I think I was always an optimistic person globally. Yeah. Locally, maybe not. Yeah. I mean, if you ask Ellie, she will say that I'm always worrying about everything. Mm-hmm. But certainly about mathematics and about these things, I was always optimistic and sort of positive. I don't know. It was. I never thought about it, but that's the way.
It comes. I mean, it comes
it's
across.
Just natural. It's just natural. And of course, what I like about mathematics, and I got to like very much, and I didn't realize that at first, is the interplay with other people. And that generates extra energy. And that generates optimism. Yeah. And two people working together. Of course, it's a question of chemistry. Yeah. Sometimes two people cannot work together. Personalities, but when they can talk mathematics together, and that takes a while to sort of develop the same language and the same speed, so to speak, and the same kind of sensitivity to the other person. There's also this question, but once that works, it's really very good, because it really helps you think. I mean, you say something and then later the other person says something, and it just all works so well. There's nothing like it. So working with students is somewhat the same. It starts off and it ends off that way. Because after a while you develop a certain degree of comfort, a certain language, and certainly with the better students and the best students that you have, you can do that. And of course, with your best students, of course, you're trying to catch your breath because they're running ahead of you.
How has math changed? I don't mean so much the organization of the subject or the number of people or anything, but just math itself is a...
It's hard for me to be objective about it because maybe what I'm saying has to do with the fact that I'm older. And therefore, I look at things differently. So it's just a function if you look at how I looked at things. I looked at them when I was young, and now I'm looking at them. I think the subject has gotten much bigger. There are many more people in the subject, and it's moving much faster. That's partly a question of communication, because first of all, there was much more solo work. And then, of course, when I collaborated, I remember collaborating with, let's say, Guido Weiss, Ray Kunze, and Tony Knapp, and people like that. Well, what did we do? I mean, we had to be in the same place. I mean, there was no fax. I mean, there were telephones, but you did very little collaboration by telephone. You could write letters, but that took days. And it was very much, and there were fewer people. So it was much more slow moving. Now everything, if you are working in a subject for which there is a substantial interest, then things move extremely quickly. And if the result is that you have papers which are collaborations of 5 or 6 people, because some group will do something and some other group, and then they'll get together. And so it moves. So it's a very different thing. And maybe the idea of sort of saying to yourself, well, let me see, what is this really about? And can I understand this in sort of, what are the basic ideas, or what's the right point of view? Maybe that gets lost a little bit. Because, on the other hand, there are things that you can do right away. And you want to do them. And in that sense, I see a lot of mathematics is done that way.
Okay, interesting. So you've described a few people. You've talked a lot about your relationship with Zygmunt. Could I ask you to pick a few people who have influenced you or whom you'd like to talk about, and just say something about your interactions with them?
What I owe to most are, first of all, my teachers, like Zygmunt, and then my students and my collaborators. I've learned, I've been the mentor to my students, but that was the beginning. But usually I've learned a tremendous amount. There's been a great deal of support to me, not just morally, but mathematically. So you're, Charlie, a prime example of that. That's been very, very important for me. An important collaboration of mine was with Jerry Folland. Jerry Folland was a student of Joe Cohn, but we talked a lot while he was a student. And then soon after he got his degree, I became interested in several complex variables. And I had this point of view about the Heisenberg group, and somehow he got involved in this either on his own or discussing. And then we started to work on things related to the Heisenberg group, and that was very, very useful. And then at about the same time, a few years later, Linda Rothschild was visiting, and I was interested in doing things not just for the Heisenberg group, but I had some vague ideas of doing things for more general Hormander type operators. And it seemed to me that what you needed to do is, like you go from Euclidean space to the Heisenberg group was one step. The general step was to go to general nilpotent groups, and then there was a theory, and then there were these free nilpotent groups, etc. So this was a very important collaboration for me. Again, what I would say about collaboration, what's so important is the idea that when two people get together, 2 or 3 people, and they really develop a stake in it, there's a tremendous amount of reinforcing that they do, and that makes a project possible. So I think it's sort of not meaningful to try to say, well, I did this and X did that, but it's... So these were some of those collaborations. Of course, my collaboration with Tony Knapp was very important. That came before that. In this unitarizability that we had to work out, this application of this Cutler-type lemma entered. So that was very important. Later on, I had a long collaboration with Phong, which was very important to me. And that, again, started off from his interest in complex analysis. You know, Phong started off by being a student of Joe Cohn. And then he sort of wrote a thesis with Joe. And he got on the basis of it, got a job at Chicago. But unfortunately, he was never able to finish that thesis. And so he got into a bit of trouble. So he came back, and I decided to take him on and work with him. And then he finished a thesis, a slightly different thesis. I don't remember exactly. Then we decided to work. And he was very interested in the D-bar-Neumann problem. And he did something very nice on his own first on finding a kernel representation for the Neumann operator. And so this was an operator, it seemed to be, it wasn't very clear, it seemed to be an operator which was a mixture of the sort of classical singular integrals and of the operators that were singular integrals but in the sort of non-isotropic sense associated to the Heisenberg group. So it was a big challenge to us, which we started to look at what kind of operators do you get this way. And then we took a certain path that led us to oscillatory integrals and to singular Radon transforms. And that was quite interesting, I think, which led us to rotational curvature. But then there was another path which I've followed more recently in work with Alex Nagel, Fulvio Ricci, and Steve Wenger on this, and I'm still working on this area of the interplay between these singular integral operators. So another collaboration which has been very important for me was my collaboration with Steve Wenger. Steve Wenger was my first student. And so we were always very friendly. I remember very clearly now, it was the year 1966. Zygmunt had organized a quarter at the University of Chicago on analysis, and he invited me to come spend a month there. And Steve Wenger was then either at Cornell or he had already, I don't remember that, or he had already moved to Wisconsin. And he came there for a week or two. So we spent a lot of time together, and he got me interested in this problem of certain oscillatory integrals which were connected with the work of Fabes and Riviere, which were connected with the Hilbert transform on the parabola. And so since then, of course, he had been my student, so we had worked pretty closely on his thesis, but since then we had started to collaborate and collaborated a lot on problems, on many things. And then, because of him, I got involved in another collaboration, because soon afterwards he said, well, you know, there is this fantastic guy in Madison. You should get to know him. His name is Alex Nagel. And so he talked about it, and then finally I met Alex Nagel, and he spent a year at the university, actually as a visitor in the 1970s, and then we started to collaborate. And after a while, the three of us collaborated, et cetera, and we've been collaborating ever since. So that's also another collaboration which has been very important to me. So I want to say, with all these collaborations, I learned a great deal from these collaborations. And there were areas that I would not have worked in if I had not been doing these collaborations. Of course, I think they learned something from me also during these collaborations, but they were they were fundamental to anything that I've done. The year I came to Princeton, I had a colleague, Jerry Waschnitzer, who came to Princeton. He came from Johns Hopkins. And the first year I was in Princeton, he and I were very good friends. Well, we were very good friends later, but we used to spend hours talking about politics, everything. So we were very good friends. And so in the spring of that year, as is the practice in Princeton, in April, you get the letter from the trustees saying what your salary is going to be the next year. And so I remember I was hired, at the time I was hired, my salary was $16,000 a year, which was a good salary, pretty good. Anyway, I received a salary increase of $2,000, which was good. Okay. That year, Bernie Dwork had already come to Princeton. He did not receive a salary increase, and he was very upset. Okay, so the idea was, Bernie was a very good friend of Jerry's, so Bernie and I were going, the chairman at that time was John Milner. And John Milner was a very hands-off chairman. He was not really interested in what was going on. He just became chairman because he was the senior guy or whatever, the most prestigious guy in the department, but he was not interested. So John Milner said, look, you two guys are concerned about this. Why don't you go see the president? Okay, so we were going to go see the Goheen at that time. And I remember it was May. It was a very warm summer day. And I knew that if you had to go see the president, you had to wear a tie and a jacket. In those days, for sure. Okay? And Bernie Dwork was coming independently. He was coming by bike. And it was a warm day, and he came in shorts and a short-sleeve shirt. Okay, that was already a little bit wrong. So we sat in Goheen's office, and he was the good cop, and the bad cop was the dean of the faculty in those days, the second in command, Dean Lester. And so we started to talk about this. And Bernie spoke first. He was senior to me, of course. And he spoke first, and he was very strong about it. And he said, this is very unfair, blah, 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 blah. You must do this. And I knew this was wrong. And I could see this wouldn't go over. So I said, well, you know, I think it is unfair, but I would suggest the following. I've been given a $2,000 raise. If it's a question of money, why don't you just give me $1,000 and give the other $1,000 to Jerry Waschnitzer? I think that would be much fairer. And they said, no. But it obviously struck a chord because right afterwards they did give him that raise. Mm-hmm. And then a few months later, they asked me to be the chairman of the department. So, because they were struck by this statesman-like. Mm-hmm. But I felt that it was not my turn, that it was Bernie Dwork's turn. Mm-hmm. So I said to Jack, who had conveyed this from the administration, mm-hmm. Jack Milner, I said, no, there are two people that are more senior than I am who should go first. Mm-hmm. Bernie Dwork, and then there was another guy who had just come back from Cornell, that was Gelfand. I said, but I thought of Bernie Dwork should be the chairman. Mm-hmm. Of course, the administration didn't want Bernie Dwork, mm-hmm. and they appointed Gelfand as chairman. Now, Gelfand was a catastrophic chairman because he was extremely mean and nasty. And so I went on leave the following year when all sorts of bad things were happening. And when I came back, things were in terrible shape. And then there were the four younger Turks decided that we had to overthrow this chairman. And so I was the leader of those people. And ultimately, we succeeded. And so I was appointed chairman. So that's how I became chairman.
Then once you were chairman, was it something like smooth sailing?
Actually, it was surprisingly easy. The department was very collegial. There was very little bureaucracy. If you wanted to appoint somebody, you just submitted a list of names to people, and it all worked very simply. It wasn't much work, and it was nice.
Your first chairmanship happened while I was your student, and so I remember that you did research and taught courses and,
yes.
supervised students.
It was just a small part-time job. Huh. It was just, that's the way it seemed. Anyway, maybe I had more energy then.
What happened the second time?
I guess they ran out of chairman, and they just turned to me. I forget why they turned to me. Yes, who was it? It was Wu Shang had been chairman just before, and Wu Shang thought I should be chairman. We were good friends. I don't know. I don't remember exactly. And I said I would take it for 2 years. It was Bill Bowen who was president then. And he said, fine, you can have it for 2 years, and then that's it. So that was also pretty easy, I thought. We were flying pretty high in those days, so it wasn't so hard.
Would it be of interest for you to describe your experiences as an editor of the Annals?
When I was an editor, I joined at the time that Burrell was the senior editor. And there were a number of editors. I think there were 4, 2 from the Institute and 2 from the university at that time. And I was an editor for about 10 years. At the time that I joined, it hadn't been formalized. I think afterwards, when I decided, I was chairman at that time, and I decided that it should be formalized and there should be terms. I forget what the arrangement was. And after that, there were terms. But before that, there seemed to be no terms. And anyway, Armand Borel thought of himself as the senior editor. And so, more or less, this was not written, but this is the way it happened. And it worked pretty well. It works pretty well. So, I mean, papers were submitted. Somehow, one of the 4 editors, or maybe there were 5 then, maybe 4, was in charge of the paper. Mm-hmm. And then that editor could reject the paper, or if he felt we should publish it, it would be circulated. And then we all had to agree. And that was not at all automatic. And sometimes we had to have meetings in which the papers we couldn't agree on would be negotiated.
Tell us something about your travels.
I traveled to a number of places. One of the places I really spent a lot of time in was in France during the academic year 66-67. I spent the whole academic year at Orsay. And actually I gave a graduate course there. And there were very good notes taken at that graduate course by two graduate students. Their names were Bachman and Somen. And I decided to write up those lecture notes in a book. So first I decided that I would just take their French notes, which were very well written, and I would try to translate them back into English, but that turned out to be impossible. You cannot do that because of the way French sentences are constructed. Besides that, I wanted to add a lot of other ideas, and that became my book on singular integrals. So that was one thing that happened. Another thing I think that is noteworthy, at least as far as I'm concerned, during that year that I was there, Carl Deleuze came to visit in the spring of, it was 67. And so we were talking, and he mentioned the following thing. He said that Laurent Schwartz, in his work on spectral synthesis, Laurent Schwartz had proved that spectral synthesis does hold, I'm sorry, I don't remember whether it does or does not hold on the sphere, and I think on the sphere in 3 dimensions. And he said he had done this by proving something about the Fourier transform of a function. If you take a function in LP for some p bigger than 1, and you take its Fourier transform, you can define its restriction to the sphere not as a function but as some distribution on the sphere. And you can do this because the Fourier transform of a radial of the sphere decays at a certain order, and that means. So he said, do you think it's possible that the Fourier transform makes sense as a function? So I thought about this question, and so then I later realized that the right thing was, the way to do it is to think of it, does it make sense as an L2 function, as an a priori inequality? And if it's an L2 function, you can use some tricks in Fourier analysis. And then there was the restriction theorem, at least for some p's. And so when I came back from France, I met this young man, Charlie. So he became my student, and I gave him a series of problems, which he solved right away. So I felt, I really now needed to give him a very good problem, and I had thought about this restriction, and I had some vague idea that this restriction theorem, of this fact that you can make these restrictions, is related to this problem about Bachner-Riesz summability. And I mentioned that I had thought about Bachner-Riesz and about the ultimate about proving things for, well, what I had proved was very partial results, and maybe one could do something close to what is the ultimate thing. So I gave that as a problem to Charlie, and of course he found a beautiful result, which was that insofar as you knew the right restriction theorem, you could get the ultimate results for Bachner-Riesz. So that was something very important that happened when I traveled. Let's see, any other travels that...
China?
China, yeah, well, I gave series of lectures there, met mathematicians, but as far as my own work,
didn't have the same influence.
No, it didn't have that same influence as this year in Paris, which had great influence. Also, yes, I traveled in the year 1970. I traveled to give an address at the International Congress, and since I had to give a plenary talk, I had to think about organizing some ideas, and that was very useful because it forced me to organize some ideas and some points of view. And those were memorable travel times.
Would you like to reminisce about our collaboration?
Our collaboration. Actually, there were two stages. I think a minor stage, which, since we're talking about it, the minor stage was the inequality of the vector-valued version of the maximal theorem. I had given a course, by the way, which became a little book, which you actually wrote the notes that were beautifully written.
By the way, I'll reminisce a little about writing the notes, but go ahead.
Yes. Okay, beautifully written. And in there, I proved some result which suggests a general result about vector-valued maximal functions. And then we started to talk about it, but of course you were so fast, and before I knew it, the theorem was proved. So that I would call our minor collaboration. Now, what was our major collaboration? Now, after your PhD, you spent a year in Princeton as a lecturer, and then you went to Chicago, which was very fortuitous for you. And I remember that you wrote me a series of letters about things you were thinking about and doing, beautiful letters in mathematics. And one of those letters was, you explained that Zygmunt, so that's interesting that it all comes back to Zygmunt, my teacher, who was there, had asked you a question which was, if I remember the question correctly, is what, in one complex variable, what is the dual space to H1?
Well, no. Okay, this
please correct me.
He asked, is there a non-trivial characterization of BMO in terms of the Poisson integral?
Okay.
So not just that on every radius that the BMO norm is uniformly bounded, but something more serious like the area integral or something.
All right. Anyway, that is makes the story even more interesting. So Zygmunt had asked Charlie a rather provocative question, and Charlie thought about it, and not only did he solve that question, but he realized that on the basis of that, one way to think of BMO is as the dual space of H1. And so he wrote me one letter, maybe it was two letters. And of course, I had been very interested in H1 and in HP because of my earlier work with Guido Weiss, and so immediately I became interested, and we started to collaborate. And then, I don't remember exactly what year that was, but at about that time, which was either 1970 or 71, we both spent some time at the Institut Mittag-Leffler in the spring. And then we talked about it a great deal. In the meanwhile, there had been some work from a probabilistic point of view by Burkholder and Gundy. And so all of these ideas were there, and then we worked on the theory of HP spaces, and we wrote this paper, which was published in the Acta and was one of my very nice collaborations. That's
definitely one of mine. I remember the same thing. I just want to add that a crucial ingredient that went into the ideas in that letter to you was a remark that you made in a paper of yours in which you remarked that BMO was a very interesting class of functions, and if you apply a singular integral to a bounded function, that's in BMO.
Right.
And so before that, there was this interesting class of functions, and they were in the exponential class. Isn't that striking? Isn't that useful? But this gave a completely different point of view.
Right. There was another thing that was very important to me that I had observed before your work on BMO, which then became part of our work, and it was understood better, was that if you took the standard class of singular integrals and applied them to L1, they did not preserve L1. They mapped L1 into H1. But if you applied them to H1, they preserved H1. And that was the dual of a statement that if you applied singular integrals to BMO, that was in BMO, which was a stronger version of that remark, which I hadn't proved, but somebody else had proved.
Let me also just tie up our collaboration with something that I mentioned earlier, the optimism. I remember we were working together, and we needed some inequality of Hardy and Littlewood, and we couldn't remember the proof, and we couldn't find the reference. And I remember very clearly you're saying, you know what? Okay, damn it, if Hardy and Littlewood could prove it, so can we.
Now it comes back to me again, and I know which inequality it is. It's the LP inequality for p less than 1, for a harmonic function and a conjugate if you integrate over the south thing. Yes, what I meant by that, I didn't mean that I was as good, maybe you were as good as Hardy and Littlewood. What I meant is that given what we know nowadays, if they could do it then, in the more primitive time, we should be able to do it now.
But it's optimism.
Yes.
You know, we can do it.
Yes.
That's
Yeah,
powerful
right.
medicine.
Right. No. That I will admit. Yes, that I will admit. Yeah, but optimism has to be part of the kit of any successful working mathematician, because you're always up against things which look hard before they're done, and then they look easier.
Yes. Yes. Oh, let me just reminisce to you about the experience of taking notes from that course. So first of all, there was a team of students taking notes from this course, at least initially. I'm not going to mention names. The lectures were so beautiful, and the notes, when I got them from the other students, were far from beautiful.
I would imagine, because I've gotten notes before.
Okay, and I took it on myself. I think I'm generally a gentle person. I kicked them off the project, and so you can. I think if you look carefully, you can see the first half of these notes are incredibly careful, and the second half I think are good, but not quite as careful, because I think it was Eugene McCarthy who was campaigning for president, and I went. I spent lots of time knocking on doors.
Yes, but they're beautiful notes. I've never seen notes. I mean, they were finished. You know, I made a few little additions and a few little changes, small changes, but they were beautiful notes. They were beautifully done.